gas lift is very high maintenance because it requires frequent adjustments. Coupled with the inefficiency in terms of work done per unit of energy consumed and the need to always have a supply of injector gas throughout the life of the project, gas lift is, therefore, used primarily when the sucker rod pumping system is not suitable. There are, however, two advantages that gas lift has over the sucker rod pumping system. Gas lift can be used in deep wells and it requires minimal equipment, so it can be readied relatively quickly. To be fully outfitted, gas lift requires only a compressor that sits on the surface, a supply of injector gas for the compressor to pressurize and then send down the annulus, a packer at the end of the tubing string, and unloading valves and operating valves mounted at varying depths in mandrels that are attached to the tubing string. Once these pieces of equipment are installed, the gas lift is ready to be brought online. Let's look at an illustration of the gas lift assembly. Here, the well has been equipped for gas lift with a compressor, packer, and various unloading and operating valves at varying levels. When put into operation, gas lift can be used to return a well to production by supplementing the natural lift. Before I continue, let me point out here that the unloading and operating valves are mounted in mandrels. Mandrels are shafts on the tubing string where tools can be mounted. Their main functions are, number one, to help maintain the pressure on the injected gas in the annulus as it makes its way down to the bottom of the hole, and number two, hold the one-way valves that enable the compressed gas in the annulus to be injected into the tubing, but that also prevent oil from leaking back out into the annulus. Since these valves in the mandrels must be cleaned periodically, two types of mandrels are available. The first is called a conventional mandrel. It is run on tubing where the valves have already been set in place inside the mandrel. Although a conventional mandrel is simpler to install, the tubing itself, along with the mandrels, must be pulled when only the valves need to be serviced and cleaned. The second, a more popular and widely used mandrel, is called a side pocket mandrel. A side pocket mandrel is hung on the tubing in such a way that the valves can be accessed for servicing and cleaning using through tubing wireline. This means that, unlike with conventional mandrels, the valves in a side pocket mandrel can be retrieved and reinserted without pulling the entire tubing string itself when the valves need to be serviced. Notice that here the side pocket of the mandrel is sufficiently offset so that there will be no restriction to through tubing wireline tools. When choosing either conventional or side pocket mandrels, it is very important to select the type that is best suited for the conditions of the well. Now let's look at how gas lift works. When injected into the tubing string, the pressurized gas from the compressor tends to form large bullet-shaped bubbles that are trailed by smaller bubbles that travel rapidly up the tubing. The initial injections of pressurized gas need to be injected in steps or stages, starting near the top of the string and then going deeper at varying multiple depths until the bottom operating valve nearest the wellbore is opened and all the other uploading valves above it have been closed. Now the well is said to be in steady state operating condition. It will remain in this condition until the well has to be killed for whatever reason, and then when production begins again, the whole process of opening and closing uploading valves until the bottom operating one is reached begins again. It is for this ongoing reason that mandrels need to be left in place throughout the production life of the well. When finally the entire hydrostatic column has been injected with gas from this bottom operating valve, a continuous gas lift operation is achieved. Remember, it is these injected gas bubbles that lighten the load sufficiently so that lift can occur. Thus its name, gas lift. Let me show you how the well gets to a steady state operating condition. To begin the process, compressed gas at the surface is released into the annulus. This pressurized gas pushes the liquid depth down as the gas fills the space. When the compressed gas reaches the top loading valve, the valve in the mandrel in the tubing string opens, letting the gas flow into the tubing string. Once in the tubing string, the gas helps to lighten the load of the heavier oil in the hydrostatic column, giving the oil enough lift from the remaining energy in the formation so that it can now be pushed to the surface. As more compressed gas is pumped into the annulus, the liquid level continues downward until it reaches the second unloading valve. As the second valve opens, the first one closes. The compressed gas in the tubing, having entered from the second uploading valve, flows up to meet the injected gas from the first valve, thus lengthening the lightened load. This lightened load again allows more oil in the hydrostatic column to be pushed to the surface. At the same time, the compressed gas in the annulus continues its downward path until it reaches the third valve, which now opens. Like the first valve, when the second valve opened, the second valve now closes. The multiple valves in the mandrels at varying depths in the tubing allow the compressed gas to enter the tubing from ever-increasing depths until the bottom of the hole is reached. When the injected compressed gas, whose pressure is helped maintain by the mandrels above them, ultimately enters the tubing string through the last valve at the bottom of the hole, the tubing string is said to be in steady state operating condition. Now with the column lightened with this pressurized gas, the reservoir pressure should be enough to push the oil in the tubing string throughout the entire hydrostatic column to the surface. Let me point out that at the surface, as the oil and gas is processed through the surface facilities, the injected gas is recaptured and recycled through the compressor and again sent down the annulus as pressurized gas. Any remaining gas not required for injection can subsequently be sent to market. Most gas lift wells follow these basic steps to get to the steady state operating condition where continuous tubing flow lift is achieved. There are, however, other configurations that can be utilized under special circumstances. The first is known as intermittent lift. Intermittent means that the lift is not continuous. It comes and goes as conditions warrant. Used in low capacity wells, it requires only an intermittent valve on the surface. When a gas line is open for a preset period, a single large slug of gas is injected down the casing through the operating valve and into the tubing. Under the right circumstances, this procedure should be enough to lighten the load sufficiently so that the oil can overcome any hydrostatic pressure and begin flowing upward. The second type of gas lift is used in dual completed wells and is known as a dual gas lift. The final type of gas lift is reserved for large capacity wells and is known as annulus flow. Unlike regular gas lift that sends the compressed gas down the annulus, in annulus flow the compressed gas is instead pumped into the tubing string where it is then sent through the valves to the annulus. To compare, the low-cost, low-maintenance sucker rod pumping system is more suitable for typical onshore wells, while the lighter, more easily installed gas lift system is used mostly offshore. There is a third method, however, that is best suited for wells that have high volume production. Known as electric submersible pumping, ESP, these sophisticated, high-performance devices are expensive to purchase, expensive to repair, and expensive to operate. Their use is, therefore, limited to high-volume applications, either onshore or offshore, where these costs can be justified. Water drive and water flood production with high water cuts are typical applications.